In a sense, algorithm plus data is equal to the trained model. So trained model is a component which accepts two inputs, which is the algorithm that you're going to apply on the data to find a pattern, a mathematical equation that can essentially solve the problem of survivors. Now, the next step that I'm going to do is I'm going to drag and drop something called a score model component. Now, the score model component accepts two inputs again. It accepts the first input as that model which has been trained, and that's what I'm going to do here. And then it is going to accept the input which is the 20% of the data. Not to worry if you have not been able to understand so far. I will try to make it crystal clear by the end of this particular exercise. And then finally, we are going to drag and drop one more component called the evaluate model. Now, this is a very important component as well. And I'm going to connect the output of the score model to the evaluate model. And I'm just going to run this particular workflow all over again. As you can see here, all the components have been run. And now let's go and explore what is score model and what is evaluate model. Now let's explore the score model. Let's look at the output of the score model and then click on visualize. The score model essentially predicts the survival status of each passenger. Correct. For every passenger that is on the 20% of the data, which is about 178 passengers, it generates two new columns called the scored probabilities and the scored labels. And if you remember, classification is a problem of probability. So any value that is going to be output is going to be between 0 and 1. And we are going to assume that any value which is above 0.5 will be marked as something called 1, and any value which is below 0.5 is going to be marked as 0. Now 1 defines that the passenger survived and 0 defines that the passenger did not survive. And as you can see here, you also have the actual survival status of that particular passenger. So you have both the predicted output as well as the actual output. Now let's look at the first passenger, 129. We do not know the name of the passenger. In reality, the passenger did survive Titanic crash. And we also predicted that the passenger did survive the Titanic crash. Now let's look at the row number 117, and let's say in this case the passenger did not survive the Titanic crash. And let's see what our probability says. And if you can see here, it also says the passenger did not survive. So far so good. So let's look at the passenger number 794. You can see here that in reality the passenger did not survive the Titanic crash, and here you can see that you're predicting that the passenger did survive the Titanic crash. And these are the misclassifications that we need to look through and iron out these misclassifications. It's time to look at the evaluate model, and let's look at the output of the evaluate model by right clicking and clicking on visualize. There will be a few metrics here, but let's focus on something called a confusion matrix. A confusion matrix is nothing but 4 quadrants. So let's understand what is positive in this particular context. Positive is the objective that we are looking to achieve. And what is the objective? The objective is we are looking to predict survivors. And hence, positive means survivors. So true positive. So true positive means the passengers truly survived, which means that the actual status is survived and the predicted status is also survived. So we have managed to predict 46 passengers right about their status of survival. Let's look at false positive. Now, remember, positive is nothing but survived. Now, I can also reread false positive as falsely identified as positive. Now, what does that mean? Falsely identified as survived, which means the passenger was dead, but we or the model that we built falsely identified them as survived, which means there were 21 misclassifications. 21 passengers were supposed to be marked dead, but our model that we built marked them survived. Now let's look at the other quadrant called false negative. Now we can also rephrase false negative as falsely identified as negative. Now if positive was survived, what would be negative? Negative is dead. So we could rephrase it as falsely identified as dead, which means there were 15 passengers who had actually survived in the Titanic, but our model did not predict them as survived, or our model predicted them as dead. And finally, we have the quadrant called the true negative, which means the passenger is actually dead and our model predicted them as dead. So in essence, this confusion matrix is going to drive the model metrics. There are a few other important metrics that are derived out of the confusion matrix. Let's first focus on the recall. Now, recall can be defined as of all the actual survivors, how many did it predict right? Now, how many actually survived? Let's have a look at it. We know the true positive, which means 46 passengers survived. And we also know false negative, means falsely identified as dead. So we know for sure that 46 plus 19 survived. And how many were we able to predict right, which is 46. So the answer is 46 by 46 plus 19, which gives you recall. Now let's focus on precision. Precision is defined as of all the predicted survivors, how many did I predict right? So of all the predicted survivors, what does that mean? It means true positive and false positive, which means that 67 passengers were predicted to be survived and we got 46 of them right, and hence the precision stands at 0.687. And this could be even shown in an Excel file as in the calculation here. As you can see here, the recall is nothing but 46 by 46 plus 19, and precision is nothing but 46 by 46 plus 21. And so what is accuracy of the model? Now accuracy of the model reflects true positive plus true negative divided by the entire number, which comes down to 0.775. In essence, you have an accuracy of 77.5%. So having so many metrics, let's understand which of them are key metrics. I would say focus on recall and precision as opposed to accuracy. Accuracy is important, but focus on recall and precision because both of them drive towards a specific objective that you would like to achieve. Let's say you focus on accuracy, and let's come out with an hypothetical matrix where your model has not been successful in predicting any survivors, which means all survivors were predicted dead. And let's say your confusion matrix looks like this. And as you can see, your accuracy is still around 51.6. Does that mean the model is good? The model is absolutely rubbish because the model is designed to predict survivors, whereas in this case it has not predicted a single survivor. This example is called a bias problem or an underfitting problem, where your data is not good enough to get any predicted output. So accuracy is not an accurate measure of the model in isolation. You need to take recall and precision into consideration when you are calculating the accuracy of this particular model. Though accuracy is easier to communicate as a metric to a customer as opposed to recall and precision. The final metric that I would like to illustrate is F1 score. And typically this metric is the metric that you will look at for evaluating the performance of the model. Now F1 score comes to a calculation of 0.697. Now let's see how is it calculated. Now F1 score, let's take this particular data point which is more realistic than the other one, and let's want to calculate F1 score. Now F1 score is nothing but 2 into precision into recall by precision plus recall. It's almost like a weighted average score, and you can see the F1 score comes to 0.696. Now for evaluating the performance of the model, other than recall, precision and accuracy, F1 score kind of is a better bet in terms of evaluating the performance of the model. So during the next iteration, if your F1 score goes up, it means your model is improving. And hence, it's a good measure to reflect the performance of that particular model.